Okay, if you look at the theorem, we want to prove it, at least sketch the proof. So if you look, point 1 is just the definition, how we define the typical codes, and point 3 is just the weak law of large numbers, which we already have this formula. It's a weak law of large numbers. Both are just small transformation. You just can take the definition, take the logarithm, and you have it immediately. The same is with 3. So what remains to, what we have to show is still 2. If you look at 2, we make the following trick. So we want to have a cardinality. But first we look at the probability that a sequence is in the typical set of sequences of Px. Of course, we can write this probability as the sum over all sequences in the typical set and sum the probabilities. Yes, now we know because of 1 that each of these probabilities is approximately the same. We can approximate it by 2 to the minus n h of x. And so we can estimate it by 1, so it's smaller than the cardinality because we take for each one the same. So we have here the number of typical sets times, and each we estimate because we want to have here the smaller by 2 to the minus n of h of x minus epsilon. Now, if you look at this equation here, this probability is smaller than this cardinality times this 2 to the minus n, and so on. But we can estimate by 3, we can estimate this. And we know that this is smaller than 1 minus sigma square over n times epsilon square. So what we just do is we can estimate this from below, and then we put all things together, and we get the result that 1 minus sigma square over n times epsilon square. Now we bring this to the other side, 2 to the n of h of x minus epsilon is lesser than the cardinality of t epsilon n of p of x. And this is exactly the lower bound for the cardinality. Now let's clear this. And now we want to prove also the upper bound. So what we do there, we know by 1, again, we use the same idea here that we estimate px of xn. We know by 1 we can estimate it by 2 to the minus n of h of x plus epsilon. Yes? So if we write now, we can write one very complicated just by the sum of probabilities. We choose all sequences in Xn and sum up its probabilities. And of course, this is bigger as if we only sum over this Xn, which are typical. So we just sum now over all sequences which are in the set of typical sequences. Px here. Pn x of xn. Now this here we can again individual estimate this. So we can estimate each sequence again. We know each sequence now has approximately the same probability. So we can estimate it again by 2 to the minus n h of x. And we count how many we have. It's exactly the cardinality. So it's a very similar trick. So we estimate this by the cardinality of the typical sets times, and now we need the other bound. We have 2 to the minus n of h of x plus epsilon here. And then, of course, we just have to bring it to the other side. We have to bring this to the other side, and we exactly get 2.